The shot was aimed outside the goal, so why did it bend back in? The ball has already left the player's foot. At this instant, it looks like the story is over. Outside the post, no chance. But the ball does not obey that straight line. Frame by frame, it bends back, it slides across the air, curls inside the post, and suddenly the impossible shot is a goal. So, what turned it after the kick? The answer is not magic, it is spin turning air into a steering force. Curious about the invisible physics hiding inside everyday motion? Follow the channel, subscribe, and keep asking what the eye cannot see. The curve starts here. A perfect center strike mostly gives the ball speed, but a free kick specialist brushes the ball off center. That one contact does two things at once. It launches the ball forward and it gives the ball rapid side spin. After contact, the player is no longer touching the ball, but the spin is still there, carried with it like a hidden instruction. Velocity says where the ball is moving. Spin says how the ball is dragging air around its surface. Now watch the air. With no spin, the flow is mostly symmetric. Air divides around the ball and the wake forms behind it. Add spin and that symmetry breaks. The moving surface pulls the nearby air with it. The boundary layer changes. The wake behind the ball tilts. That tilted wake is the clue. The ball has redirected air sideways, so the air has gained sideways momentum. And momentum does not appear for free. If the ball pushes the air one way, the air pushes the ball the other way. That reaction is the Magnus force. It points sideways, perpendicular to the flight direction and tied to the spin axis. A compact way to remember the direction is omega cross v. The important part is that this force is not a single kick in midair. It keeps acting while the ball is spinning and moving. Tiny sideways pushes over the whole flight become a visible curve. Here is the same shot as a simple model. Without the Magnus force, the ball follows the red reference line and misses. Now add drag, weight, and the sideways Magnus force. The ball still moves forward, but at every moment, the air nudges it sideways. The path is not a corner. It is not a sudden turn. It is acceleration. Each green arrow is small. Together, they bend the whole trajectory until the ball crosses back inside the goal. That is why the kick can aim outside and finish inside. From 1930 to 2026, the official World Cup ball changed from tournament to tournament. Leather panels gave way to new shapes, new seams, new materials, and new surface textures. Now, meet this year's ball, Trionda, the official match ball of the 2026 World Cup. And there is a deeper twist. The ball is not just a sphere, it has seams, panels, texture, and sometimes tiny engineered patterns. Those details change the boundary layer, where air clings, where it separates, and how the wake forms. That is why World Cup balls can feel different to players. A smoother ball, a rougher ball, a different seam layout. Each one can shift the aerodynamic behavior. The design changes what the air can do. Now look closer at Trionda. Its 4-panel construction is a bold geometry choice. The surface texture, grooves, and seams are not only decoration, they are part of the aerodynamic design. In this simplified graph, speed runs from left to right, while drag rises vertically. The dip marks the drag crisis. The boundary layer changes, the wake narrows, and drag falls. Surface texture can shift where that transition happens. Wind tunnel studies of Trionda compare its roughness and drag behavior with recent World Cup balls. The exact flight in a match still depends on speed, spin, altitude, humidity, and the strike itself. But the big idea is clear. Panel geometry and surface roughness help decide how the boundary layer transitions and how stable the wake becomes. The ball's look and the ball's flight are connected, so the curved free kick is a chain. The player strikes off center. The ball leaves with velocity and spin. The spinning surface redirects the air. The wake tilts. The air pushes back, and the Magnus force keeps steering the ball as it flies. That is why a shot can start outside the goal and come back inside the post. Not because the ball decides to turn, because spin makes the surrounding air push it there. A free kick curves because spin turns air into an invisible steering force. Thank you for watching.